Okay, this is a free response question over polar coordinates. So this is from the AP sample questions from Unit 5. So here we have two graphs, looks like some sort of a lemison and a circle, and it is asking us to find the area of the shaded region inside the circle and also inside of the lemison. So this area here, they have it shaded for you. And when I looked at this, I try to use symmetry as much as possible. Now, normally, when I do symmetry, I usually start at theta equals 0, and then I do my sweep, from there. That's not going to work here, though, because this is symmetrical, left half, right half. So I might have to kind of adjust things from there. So I'm going to attempt to use symmetry, and so because I'm using symmetry, I'm going to have to double my answers, so that's why this 2 is out front here. And so the way I saw it, and I'm trying to find something, maybe a paper clip would work. So what I'm going to do is I'm going to try to find the right half. So instead of sweeping, normally I sweep from 0 up. Well, instead, I'm going to have to start sweeping down here. So notice that the circle is kind of what I'm guiding. So I'm sweeping, sweeping, sweeping. The circle is still guiding the behavior. The circle, the circle, the circle, the circle, until I get to there, that intersection there. So I'm going to find this area right there. Okay, so that'll be 1/2 the integration. And since I started down there, I'm going to call that negative pi over 2. And then I'm going to have to sweep up until that intersection. And I don't actually need to calculate that intersection by hand. It told me in the problem that they intersect at pi over 6. So I'm going to integrate from negative pi over 2 to pi over 6 from there. Plus, then I'm going to integrate the next piece. So when I integrate from there, I'm going to be sweeping, sweeping. Notice this time the lemison is kind of guiding the behavior until I get to the top. Okay, and when I mean top, I mean really pi over 2 there. So then I'm going to integrate from pi over 6 to pi over 2 of the lemison. And again, that's just that area formula. Remember that area formula is 1/2 the integration with your bounds of whichever piece that's kind of guiding the behavior, quantity squared. So I have this. And this is a calculator active question. So I have that typed into my calculator there. So I did the first piece. And again, you're going to hit math 9 to get those bounds. And I could have had the parentheses in there, but 3 squared is just 9. So that one didn't matter. So I've got this as 2. And I didn't cut that in half. Or you can say, well, this half distributed is going to get rid of those. Or I'm sorry, this 2 distributed is going to get rid of those 1/2s. So either way, you could have that 18.8, and that'd be 50 divided by 2 plus, and just in case you didn't know how to do that again, you hit math 9, and then I'm going to put the other bounds in there. It was pi over 6 and pi over 2, and then I'm going to do 4 minus 2 sine theta. Close that up and square it, d theta. So you type that in and you get this 5.59 number. So plus 5.859. And again, that's over 2, so you have this. And again, you could say, well, I'm just going to distribute the 2 and then add those two things together. And after some math, I got a final answer of 24.709. I didn't write down how many points that was worth. Out of the 9 points, it was probably worth 3 or 4 points. So hopefully you were able to collect all those points for Part A. All right, so then moving on to Part B. Part B says the particle moves along the polar curve. Okay, so it's kind of on that lemison. And the time gives us theta equals t squared. Find the time over the interval from 1 to 2 when the x-coordinate of the particle's motion is -1. So they're talking about the x-coordinate, and I know when I'm dealing with polar that x is r cosine theta. So let me just scooch this up here. So when they're talking about polar, I know that x equals r cos theta. That's one of our formulas. And now I have an r value, and then they're also asking me to plug in theta equals t squared from up there. So you can kind of say, when I plug that in, so r is 4 minus 2 sine theta cos theta. Okay. So we have this, and then, so we've got that, and now I'm going to plug in, since theta equals t squared, I'm going to plug that in. So I've got 4 minus 2 sine t squared multiplied by cosine t squared. Okay, and I know another piece about that. It said that for which the coordinate of the particle's position is -1. So the position is -1. So I know that this has to equal -1. So we're going to say -1 equals 4 minus 2 that t squared cosine of this. So what I'm going to do now is I'm going to put those into my y equals, because I want to know when those two things are equal. So I'm going to go ahead and make, this my y1, and I'm going to plug that into my y2 on my calculator. You're going to find out, though, that that is actually not going to work because you can't find the intersections. You're like, well, how am I going to solve this thing? So my suggestion to you, instead of doing this, I would move this to the other side, okay? So when you try to do that in your calculator, you'll see that when you try to do like second calc intersect, it's not going to work. It's not an option. So what we're going to do is we want this, if we add 1 to both sides, we'll go like this. And now, the other thing you need to realize is that now we're in t's, so we need to switch our calculator back to function mode. So hold on, I've still got this here, and then it'll be a +1. So you've got this. Now you can put this in your calculator under function mode, okay? So you just type it in there, just watching your parentheses, and then when you graph it, you're going to get this big old mess. But remember, we want to restrict it, so maybe our window, we just go from -1, and it was from 1 to 2. So really, from -1 to 2.5 should be more than enough of a window for us to see what we need to see. And then once it graphs in there, we want to find where it equals 0. So that one looks like it's going to be outside the window. So I want this one. And again, I just adjusted the window. So second calc now intersection is a choice. So we're going to do second calc intersect. And, oh, it didn't like that. Graph that. So second calc intersect. Where am I? So let me arrow till I see my little cursor. Oh, that's because I don't want to I didn't graph y equals 0 on it. Or you could have just found the zeros. You could have found the zeros. I forgot to graph y equals 0. So second calc, I'm going to do intersect. There's my cursor. We'll hit enter, enter, enter. And again, you could have done second calc zeros. And I got 1.4279, so I'll call that 4.278. Okay, so here I got 1.42, and then we'll call it 8 right there. Okay, so we've got that as our part B solution. All right, so now we are going to move on to part C. Okay, so in part C, they are asking us about the position, or to find the velocity vector at 1.5 and the position vector. So hopefully you know that the position vector, we actually already have part of it, right? So the position vector is given from this part up here, or I guess you could do this part right here. So that'll be the x-coordinate. So remember that position is the x-coordinate at time, and then the y-coordinate. So once you get to there, you're like, well, I already have this one, right? So my position vector is going to be 4 minus 2 sine t squared cos t squared, and then watch your parentheses there. Okay, so there's the x-coordinate, comma. Now the y position vector, you might have to do a little work for. Well, if we know that y, right, equals r sine theta, then you're just going to use that very similarly. So we have that r value again, so we've got 4 minus 2 sine t squared. It'll be just like before, so there's the r plugging in t squared. And then also then I need the sine. So then it'll be sine t squared. That'll give you the vertical component of that. Okay, so then there is the vector, and now we want to evaluate and take the derivative to get to position, because we know that velocity is the derivative from the position. So once you have this position, basically you want to plug in. So the velocity at 1.5, right, is going to be the derivative evaluated at 1.5 of the x, and then the derivative evaluated at 1.5 of the y. And you can use Math 8 as the feature on your calculator. So I'm still in function, so if you do it with the x, you get that. So there is my x1, and then I will type in the y1, so you're going to do Math 8, and now I need to type in that same thing, but only whatever the y coordinate was. So just watch your parentheses. 4 minus 2 sine, and then that thing squared, close parentheses, close that, and then another set of parentheses. Oh, am I out of my parentheses? And then sine of t squared or x squared, close, close, arrow over, and I'm evaluating that at 1.5, and I get a negative 1.67, we'll call it 3. Okay, so then you just write those in your vector, and then you should be all done. So my final answer, negative 8.072, comma, negative 1.673. And I'll close that up, and hopefully, oh, you can't even see it. Okay, and there's my final answer for that.